Area under the curve. So given some function like this, we can solve for the area. We're going to talk about the row method in a minute. Let's just talk about with columns first. So what we can do is we can construct a little column of width dx, okay, and it has a height of let's call it h for now. Okay, it has a height of that. So the area of this little column dA, let's call it, right? The d means infinitesimally small. So instead of being, delta A, it's d because delta x is going to be infinitesimally small. It's going to be the height, height times base, h times dx, right? So that's the area of this thing. And what we want to do is we want to really do a whole bunch of them. We want to add them all up, right? If we could somehow add up all these little columns that would be infinitesimally small, we would essentially be adding up lines. We would essentially be adding up a whole bunch of lines that would be all right next to each other, and we have each individual height. So the height would have to change as a function of x, given an x value. If x is over here, or if x is over here, or if x is over here, or anywhere, height would need to change for this column. And if I could add all those things up, I would get the area. Okay, so let's do it to here. Let's just do it to this limit right here, to the value of 2. Okay, let's integrate, and that's what the integral does. The integral sums up all these values. It adds them all up. So we integrate. We're going to integrate from here is going to be the area, okay? And this one we're going to integrate in terms of x. So this one's going to be in terms of a, so we're going to go from 0 to a. Okay, you don't usually write that. And this one's going to go from 0 from the x value. We can go beyond that too, but let's go from here. Let's go from here, from 0 all the way to 2. So we're going to integrate from 0 to 2, and we're going to integrate from 0 to a. And now we just solve this integral. So the integral of 1, that's really, everyone gets a little confused with this. The integral of 1 dx, what is that? Well, that's just equal to x. Okay, what about the integral of just dx? Well, it's just 1. I just didn't write down the 1, so it's still x. So now if you know that, then the integral of dA is going to be equal to a. Okay, so from 0, it's from a, then you put an a into 0, it's going to be a. This integral is a little more harder to solve because we need to put h in terms of x. Okay, because we can't, so we need, remember I said this x has to be a function, this h has to be a function of x. So given an x value, it has to change. Okay, so what we're going to do here is we usually need to know our function. We need to know the function, right? It's usually given to us y as a function of x, right? Some function of x. And y tells us the height, right? Given an x value, it tells us the height. So in this case, for this simple case, for this area under the curve where x-axis is our lower bound, we could just use h as our function. So this would be just the integral from 0 to 2 of our function, whatever function that is, dx. Okay? These get more and more complicated as we add another function underneath it, right? We would subtract the two functions, okay? And there's also other methods of solving if you have rows instead of columns. So sometimes it might be beneficial if you have a function that might look like this, and it looks like this. Instead of doing two integrals, because this height here would be different than this height here in terms of the function used, you could also just use rows, okay, instead of setting it to dy, okay, and with a w of a width. But everything else is pretty much the exact same concept. Okay, so that's all we're doing is we're just making little columns, calling it dA, integrating to add up all of them, and making sure that your limits and your function is all in terms of the variable needed, right? So this is in terms of dx, and this would be in terms of dy.